Thank you for being here, everyone. In today's session of usage of hydrocarbons, the ammonia process. Today we have two representatives from Point Lisa's Nitrogen Limited, Mr. Khellon James and Mr. Visham Gobadan. So I have the bio information here for Mr. Khellon James, so I'll begin. Khellon James is a graduate of the University of Trinidad and Tobago with a Master of Engineering degree and is currently employed at Point Lisa's Nitrogen Limited, where he has worked for the past 5 years. Point Lisa's Nitrogen Limited operates a world-class ammonia plant in North Caspian Drive, Point Lisa's Industrial Estate North. The Point Lisa's Nitrogen Limited fertilizer complex is the first facility to be located in the new Point Lisa's Industrial Estate North. The plant was constructed by Kellogg, Brown and Root Inc., formerly the M.W. Kellogg Company, and began production in April 1998. Khellon has worked alongside his fellow process engineers on several projects, all geared towards the sustainable and efficient operations of the plant, and has been actively involved in plant turnarounds, incident investigations, and troubleshooting exercises and hazard analysis. As management of change MOC coordinator, he was responsible for making significant improvements in the efficiency of the MOC process and procedures. Khellon has a special interest in design and simulation and has obtained certifications in AutoCAD Fundamentals 1 and 2, Aspen Plus simulation software, and Aspen heat exchanger design and rating. Mr. James, the floor is all yours.
All right, thanks for that, Brian. So I'll just jump right into the presentation. I hope you guys can hear me clearly. So the talk today is on the non-fuel uses of natural gas as it relates to the ammonia production process. What I should say, as Visham was mentioning, is that the primary use of the natural gas at Point Lisa's Nitrogen is really as raw material for the synthesis of ammonia. And I only talk is really on non-fuel uses, but we do use the natural gas as a fuel on the facility for various processes, and we actually cannot produce the ammonia without using the natural gas as a fuel, and I'll explain that a little bit in the successive slides. So just some introduction or background on the facility. So Point Lisa's Nitrogen Limited is at 2040 short ton per day, which translates into about 1850 metric tons of ammonia. The process is based on the low energy natural gas reforming or CAP technology, CAP meaning Kellogg Advanced Ammonia Process, which is offered and licensed by M.W. Kellogg. We produce the ammonia and we store it at minus 28 degrees Fahrenheit in 2 storage tanks. Now the natural gas that is supplied to PLNL is supplied by NGC or Gasco. The natural gas is first supplied to PPGPL, where any condensate or heavy ends is removed before routing it to PLNL for internal distribution to the various users. What I should mention though, the reason that we utilize the natural gas is because, as some of you may know, natural gas, the primary component is methane gas or CH4. And ammonia being of the chemical formula NH3, we require or we remove the hydrogen component from the methane gas and react it with nitrogen in order to produce the ammonia. Right, so the ammonia process could be broken down into the following processes, being raw synthesis gas preparation, synthesis gas purification, ammonia synthesis, ammonia refrigeration and storage, and purge gas recovery. Right, so in the synthesis gas preparation step, that could actually be broken down into four major steps, which are the desulfurization of natural gas, primary reforming of the natural gas, secondary reforming of the primary reformer effluent, and CO2 shift conversion. Right, so in the desulfurization section of the plant, this is where we basically remove sulfur compounds that are inherent in the natural gas that comes onto the plant. We must remove these sulfur compounds because they act as poisons to the downstream catalysts. So this desulfurization takes place via two desulfurizers. We call them the 108DA and 108DB. They operate in a lead-lag manner. They could, however, be operated in parallel mode. If you look at the diagram on the right here, this is basically how it's configured. The first bed, the 108DA, that is comprised of two types of catalysts, the NEMO catalyst or nickel molybdate and a zinc oxide catalyst. The second bed is comprised of a copper oxide catalyst and a zinc oxide catalyst. So basically what takes place here is two reactions, the hydrogenation reaction, and we also have adsorption. So in the lead bed, which I mentioned contains the nickel molybdate catalyst, that is the hydrogenation catalyst, and we have the zinc oxide catalyst, which is the adsorption catalyst. So the reactions on the right basically depict what goes on. So you have the organic sulfur compounds, you have mercaptans, carbonyl sulfide, which basically is reacted with hydrogen over the NEMO catalyst to give you hydrogen sulfide, right? And then in the second reaction, the adsorption reaction, the hydrogen sulfide is adsorbed onto the zinc absorbent material. The second reaction, well, in the second vessel, we have the copper oxide catalyst, which could also act as a hydrogenation catalyst. And we have the zinc oxide catalyst, and the lag bed is really there to clean up any residual sulfur compounds that came over from the first bed. But the first reactor really does the bulk of the work. So the reactions are basically here. You see the copper basically removing the sulfur components in the second bed, in the second reactor rather. Right. So the primary reforming reaction, this is probably one of the most important steps in the process, because this is where we actually get the hydrogen from. As I mentioned, the natural gas is comprised of CH4. So this is where we basically extract the hydrogen, right? And that is done by a mixture of compressed natural gas and steam being passed over a nickel catalyst, where the reaction takes place in catalyst tubes. The end result is that we get about 66% hydrogen. And of course, not all of the natural gas or methane gas is converted to hydrogen. So we end up with about 14.4% methane gas leaving the primary reformer. So two main reactions take place in the reforming step. We have the steam reforming reaction, where we react the methane with steam, as I mentioned before, to give you carbon monoxide and hydrogen. And we have the water gas shift reaction, where carbon monoxide is reacted with the steam to give you carbon dioxide and hydrogen. Now you'll notice in the first reaction, which is denoted by a plus sign here, that the reaction is highly endothermic. And the second reaction, denoted by a minus sign here, meaning that it gives off heat, is an exothermic reaction. Now the net reaction is endothermic, and therefore we need to supply the reaction with a source of heat in order to drive the forward reaction, right? So that comes back to one of the other uses of the natural gas, which is as a fuel in order to supply heat to this reaction, right? And the next slide will show that. So here the heat of reaction is supplied by 96 down-fired arch burners, right? Where when natural gas is actually utilized as a fuel in order to produce the flame that you see here, that provides the heat. These black rows here are basically the catalyst tubes, where the nickel catalyst is stored, and you have the gas flowing through and the reaction taking place inside of the tubes. All right, so secondary reforming. This step also is very important because this is where we get the nitrogen component. So what we do is we inject air into the secondary reformer, air being comprised of nitrogen and oxygen, about 79% nitrogen and 21% oxygen. Again, the nitrogen is what is required for the ammonia synthesis, the nitrogen and the hydrogen, right? So this is where we inject the nitrogen. We also inject the oxygen here. The oxygen in the secondary reformer is used for combustion, right? And you'll see why in the next slide. The result is that partially reformed gas from the previous step, the primary reformer, is further reformed. You want to get a 14.4% methane gas down to about 0.4% methane gas leaving the secondary reformer. All right, so again, sorry. So two reactions take place in the secondary reformer. So we have the combustion reaction, as I mentioned, where methane gas, some of the methane from the primary reforming step, and hydrogen reacts with oxygen in the combustion chamber, and that is where this reaction gets its heat from. Because again, reforming takes place in this reaction, and that reaction requires heat. So this reactor is what you call an autothermal reaction, whereby it provides its own heat to drive the reaction. And that heat, again, comes from the combustion of the methane gas with oxygen, right? In this vessel, we also have nickel catalysts, like the primary reformer, and it's basically the same reaction that takes place here in the secondary reformer, with the result, the exit gas having about 0.4% methane gas. All right, so this is just a diagram of what the secondary reformer looks like. We introduce air, which has the nitrogen and the oxygen. We introduce some more steam for the reforming reaction. The gas comes in here from the primary reformer. We have the combustion zone, which provides the heat for the reaction. We have the bed of nickel catalyst. We have some refractory. It's also water jacketed, because this process actually could go up to about 1800 degrees Fahrenheit to about 2000 degrees Fahrenheit. And it's actually one of the hottest processes on the plant. So it's water jacketed and refractory lined, right? And the CO2 shift conversion step. So what you would have noticed if you was paying attention in the primary reforming step and the secondary reforming step, we actually produce some carbon monoxide. Now the carbon monoxide acts as a poison to the ammonia conversion catalyst, so we must remove it. And how we remove it is via the shift conversion step, where we have two reactors. We have the high temperature shift reactor, which has an iron-based catalyst in it. And we have the low temperature shift reactor, which has a copper-based catalyst. Now, in the shift conversion step, the reactions that take place, or the reaction that takes place, is carbon monoxide being reacted with steam to give you carbon dioxide and even more hydrogen for the synthesis of ammonia, right? In the HTS, or the high temperature shift, it's a rate-based reaction, which reduces the carbon monoxide from 13% down to about 3.3%. And in the LTS, or low temperature shift, it's an equilibrium-based reactor, and it reduces the carbon monoxide down from the 3.3% down to 0.3%. Another thing to mention here is that this reaction is an exothermic reaction, meaning that it gives off heat, right? And the first reactor, the HTS, that takes place at about 700 degrees Fahrenheit. Now you'll notice in between these two reactors, we have a cooling step, and it's because the reaction is exothermic. So this actually generates heat. You come out here about maybe about 840 there about degrees Fahrenheit, which we then need to cool down for the low temperature shift reaction, all right? And we cool it down to about 400 degrees Fahrenheit. Right, the next step in the process is CO2 removal, right? And well, this section here really deals with synthesis gas purification, right? So if I could recap, in the previous step, it was the preparation of the synthesis gas, right? Whereby we introduce the nitrogen, we get hydrogen from the reforming step. But we did produce some carbon monoxide, which we converted to CO2. But now you need to also remove the CO2 from the process, because CO2 is also a poison to the ammonia synthesis catalyst. In this step, we also have methanation and we have molecular sieve drying, and I'll basically break those down later. Right, so in the CO2 removal step, as I mentioned, CO2 is a poison to the ammonia synthesis catalyst. So what we do is we basically introduce the CO2 into the ammonia, the CO2 absorber, whereby it's contacted with a solvent, which is called Benfil or potassium carbonate, right? Basically, the reaction that takes place here is the potassium carbonate basically absorbing the CO2 to give you potassium bicarbonate. And one thing I should mention here is that it isn't just potassium carbonate. The Benfil solution is really a mixture of water and the potassium carbonate, being about 27 to 30% potassium carbonate. So looking at the diagram, what happens here is that the gas is introduced at the bottom of the absorber. It flows upward and it contacts the Benfil solution that flows down, right? Leaving the absorber is what we call rich Benfil because it's rich in CO2. That rich Benfil, it then goes to the stripper where it's contacted with upward flowing stripping steam. The steam essentially strips the CO2 from the Benfil, the rich Benfil, after which it is called lean Benfil. That lean Benfil is then recycled back to the CO2 absorber to continue the absorption process. The result is about 0.1% carbon dioxide leaving with the processed gas. And of course, we vent that CO2 to the atmosphere. Right. In the methanation step, any residual carbon monoxide and carbon dioxide from the previous step is converted back to methane and water. Remember, this step is really important again because the carbon monoxide and carbon dioxide again are poisons to the ammonia synthesis catalyst. At the end of the methanation step, we have about less than 5 ppm carbon oxides leaving in the synthesis gas, which is good. All right, so the reactions that take place here, two reactions basically. We have the carbon monoxide reacting with hydrogen to give you methane and water. It's done over a nickel-based catalyst. And we also have carbon dioxide reacting with hydrogen to give you methane. Now, these reactions are highly exothermic. Just 1 mole% of carbon monoxide would raise the temperature by 133 degrees Fahrenheit. And just 1 mole% of CO2 will raise the temperature by 108 degrees Fahrenheit. So from this, you could see why the previous steps are so important, meaning the shift conversion step, the CO2 shift conversion step, and the carbon and the CO2 removal step. Because if you have high amounts of carbon monoxide and carbon dioxide coming down to the methanator, you could raise the temperature significantly. You could cause the methanator to burn down, which could leak out explosive hydrogen gas. So molecular sieve drying. So you would have noticed in the previous step, we produced some water. Water is also introduced in the form of steam, right? Now that water is also a poison to the ammonia synthesis catalyst. Anything basically that has an oxygen component in it is a poison to the ammonia synthesis catalyst. But I think what happens is the oxygen, it takes up or blocks the active sites on the catalyst, thereby making it inactive and reduces the production of ammonia. So that really the reason why we want to remove all of these oxides from the process. So what happens here, the synthesis gas is passed through one of two molecular sieve dryers. One of the dryers is in absorption mode, while the other is in regeneration mode. Right? X the molecular sieve dryers, we have about or less than 0.5 ppm of moisture. Right, and the most important step, the ammonia synthesis step. Now, if I could recap, we got our hydrogen, we did produce some CO2, we removed that, we had some water in the process, and we also removed that. So the result is synthesis gas, which is really hydrogen and nitrogen. The gas is free of moisture, it's free of all the carbon oxides. And what we do in this step is we basically compress that synthesis gas and we direct it to the synthesis converter, right? The reaction that takes place here is 3 moles of hydrogen reacting with nitrogen. You give it 2 moles of ammonia. The reaction again is highly exothermic. and it's done over 4 catalyst beds. The first bed, the largest bed, being a magnetite bed or iron-based catalyst, and the other 3 beds are ruthenium-based catalysts, right? So if I could describe this process, so basically, as I mentioned, we have compressed synthesis gas coming into the loop. What you will notice is that synthesis gas that comes into the loop is heated up by the gas that actually leaves the converter. Because this reaction is exothermic, you have a lot of heat being generated, and that heat is actually used to heat up the incoming gas, right? That gas is then further heated up in what we call interchangers, right? So again, this process is exothermic, so the reaction across each bed produces heat. That heat is what we use to heat up the incoming gas even further. And these 2 streams, so basically a split, the stream is split. It goes into one of the interchangers here from the second bed. It picks up heat, and the other stream goes into the third interchanger at the third bed and picks up heat. Those 2 streams join back and go to the top of the first bed. And then, of course, you have the exothermic reaction taking place here. Now, the first bed, as I mentioned, is the biggest bed, and it takes place over iron oxide catalyst, and we get about 9 to 10% ammonia being produced here. The second bed produces about 4% ammonia, the third bed producing about 3%, and the last bed producing about 2% ammonia. You'll notice now, as I mentioned, the exit stream here coming off with a lot of heat. It's cooled, and that cool stream is actually used to cool down the increase in temperature from the first bed. So that heat, the heat that it picks up, then goes to boil water here to produce high pressure steam, right? One thing to mention here, as I mentioned, the natural gas has other uses, right? So during the startup of the synthesis loop, we don't have any heat because the reaction isn't started. So in order to bring the incoming gas up to the reaction temperature, we actually utilize a startup heater, which uses natural gas as a fuel to heat up the gas coming in. So that's another use of the natural gas in the facility. Okay. The ammonia synthesis reaction is an equilibrium limited reaction whereby we only produce about 17 to 20% ammonia per pass. And that is the reason why we recycle from the refrigeration system back to the converter. We recycle unreacted components back to the converter in order to maximize production. Right, so onto the ammonia refrigeration section. Basically what happens here, liquid ammonia with unreacted syngas, the hydrogen, nitrogen with some methane and argon are collected. The synthesis gas X the converter is cooled, allowing ammonia to condense. Compressed ammonia vapors are cooled and condensed. And then what we have taking place is purge and flash gases being sent to the purge gas recovery section. So the result of this section here, this is basically where, if I could simplify it, is where we basically cool and condense the ammonia product, which is then pumped, if you look at the diagram here, to the ammonia storage tanks. So what happens here, this vessel is called a unitized chiller. So it has 4 units, and in each unit basically operates at a different temperature and pressure. As you go on to the successive stages from, well, this is really the 4th stage, 3rd, I know I have it wrong side, but it's really 4th, 3rd, 2nd, and 1st stage. The pressure is reduced and the temperature is reduced in each successive stage down to minus 28 degrees Fahrenheit, where the product is drawn off from to the ammonia storage tanks. In this step, you also have the recycle here, this stream goes back to the synthesis converter, and that is really to get the unreacted hydrogen and nitrogen going back to the converter to maximize your production. This stream here is a purge gas stream, and I'll explain that, what is the purpose of that in the next slide. So in the purge gas section, again, we have unreacted hydrogen and nitrogen, but we also have some inerts in the loop. Remember that we had produced some methane gas, and we also had some argon that comes into the process with the natural gas from the beginning. Now, the methane and the argon are inerts, right? So they don't really do anything in the reaction except to take up space, right? And because we recycle, those gases could actually cycle up in the converter and basically reduce the amount of reactants that you have to produce ammonia in the first place. So in the purge gas recovery unit, what we do is we separate the hydrogen and nitrogen, valuable hydrogen and nitrogen, or your syngas, from the inerts, methane and argon. And the result is basically recycle syngas, hydrogen and nitrogen, back to the converter, and methane gas go into the primary reformer as secondary fuel, right? So I should basically explain this. The 96 arch burners that I talked about that were used for the generation of heat in the primary reformer, some of the fuel that is used there isn't just the natural gas that comes on, it comes into the plant. It's actually secondary fuel, which comes from the purge gas recovery unit. Right, so just to summarize the other natural gas users at PLNL. So I mentioned before it's used as fuel in the primary arch burners in the primary reformer. It's used as fuel to the tunnel burners in the primary reformer. And the tunnel burners is what is responsible for additional heat to the flue gas. And the flue gas is really the result of the combustion reaction that takes place in the primary reformer that supplies the heat to the reaction. So the flue gas is that result or the exit gas from the combustion reaction. We actually use that flue gas to heat some of the other processes, well, in the process, right? So it's used to heat high pressure steam. It's used to heat the air that comes onto the plant. It's used to heat the combustion air. And it's also used to preheat the natural gas feed that comes onto the plant, right? So we actually supply that flue gas with additional heat via the tunnel burners. We also use natural gas as a fuel in the package boiler for the generation of medium pressure steam. This is a very important step because we use the steam in the primary reforming reaction, and we also utilize medium pressure steam to drive the various turbines on the plant. We also use the natural gas in our flares to burn any vented or built up gases in the process. And as I mentioned before, we use it in the startup heater to provide heat for the ammonia synthesis reaction at startup. So uses of ammonia. So the ammonia that we pump to the storage tanks, we basically supply it to ships at the port of Point Lisas, after which it is sold on the international market for the following uses. The primary use being as an agricultural fertilizer. In the US, about 80% of the ammonia that is produced is actually used as a fertilizer. It's also used as a refrigerant. It's also used for the manufacture of plastics, purification of water supplies. It's used for the manufacture of explosives, textiles, pesticides, and other chemicals. And you could also find it in your household and industrial cleaning solutions. And that is it for the presentation. Visham could take any of your questions at this point.
Thank you very much, Mr. James. So any questions? We have some questions in the chat here. What is the largest percentage, this is from Adrian, what is the largest percentage of ammonia used for?
So meaning in the uses of ammonia after we sell it?
I'm not sure.
Brian, if I could answer it this way, we don't actually do anything with the ammonia we produce.
Our
final product is ammonia. We don't have any downstream uses for ammonia. For example, some of the neighboring plants, they would have like I don't know how many of you all would be familiar with the AUM complex. They actually take the ammonia and would do other stuff with it, like produce UAN, melamine, which is some of the other downstream processes. But for us, it stops at the production of ammonia, which is, as Khellon is saying, is exported, totally 100% exported as final product.
Okay. Right. Another question. This is my question. What is Point Lisa's Nitrogen Limited view and or their progress with CO2 sequestration for this, the 0.1% of the CO2 that is vented?
We could talk about that one?
Well, I could answer it this way, Brian. Basically, you remember we have this whole green energy thing in Trinidad now, and PLNL is actually on board with that. We actually have a representative, which is one of our process colleagues, who actually takes part in all of these meetings with the different stakeholders in that whole CO2 recovery, green emission project as well in Trinidad. So yes, we are on board with it. In terms of the progress, we would have had initial talks with different stakeholders with regards to that, but there's nothing really conclusive. I don't think that even at the government level, there's anything conclusive as yet. They would have set out guidelines, which we are basically trying to follow, and are coming up with plans right now to see how best. So it's really a matter of strategy for now, Brian.
Okay.
Yeah. So it's nothing in the, if you want to say in the near future, but it's really on a more high level strategy kind of discussion right now.
Understood. All right.
Yeah.
Another question here from Evangeline. Do you think there would be any alternative means to use instead of natural gas in the ammonia process? So do you think there would be any alternative means to use instead of natural gas in the ammonia process?
You mean as a raw material? I'm not too sure the question.
Yeah, I think what she's saying is, Visham, instead of using the natural gas for hydrogen, if there are any other sources of hydrogen. I think there's a facility, Visham, I think Alicia had shared it in the group one time, where this company is actually trying to, I think, get the hydrogen from, I'm not too sure.
Is it biofuel? I think it was.
And I don't think it was biofuel.
Yeah, I know they had talks about using things like biofuel as a source of methane, but then the quantities that are required to produce the amount of ammonia we do would be a challenge. There were some other projects like that, basically along those lines, for actually finding different sources of hydrogen. So you're right there, Khellon.
Yeah.
Yeah, there are other options, but for us, we basically right now, because I guess of the price of natural gas in Trinidad, it's so affordable that our shareholders and stakeholders decide to keep
the incentive.
Yeah, keep using natural gas as the as our main raw material until, I'll have to say it this way, until further notice.
Okay. Yeah. All right. I have another question here. To what extent is, now this might be a little off of the topic, but it's still in relation. To what extent is digitization and artificial intelligence implemented in Point Lisa's Nitrogen Limited's processes? That's a big one these days, and a lot of us, we have interest in, learning.
All right, so if I could take that, one of the initiatives that we're working on right now is related to the MOC process. So we're actually looking at digitizing that via the use of software to carry out the MOC process. So in the past, and we would have basically, it would have been a paper-based sort of system where I don't know if you guys know exactly what is MOC, but it's really management of change. And basically what that is any change that is done on the plan, we have to document it, and it must be approved. So what we would have done is generated paper-based documents, which would be passed from desk to desk in order to get the MOCs approved. So what we're embarking on right now is getting a software that could basically make the process more efficient. That's one of the ways we going into the new digitization age.
Yeah, I think Brian, to just build on what Khellon is saying, the world is moving in terms of I guess new technologies, new innovative ways of doing things. I guess COVID in 2020 would have actually forced a lot of people to find new ways of doing things and becoming more innovative in doing things. And I think coming out of this experience in this year, we definitely will, I think, probably put even more focus on expanding on some of the things. And Khellon just give you one example. Another example which we have been actually working on is, like remote data recovery from our DCS. Well, not data recovery, but data interaction from our DCS system. Remote monitoring of the plant is something that is also being looked into. But there comes the negatives with those things as well too, which is things like cybersecurity and just making sure that we don't end up in a situation that we don't want, right? But definitely digitization, moving with the times with technology is the way that PNL will want to go.
Okay. So you mentioned
if I could just share something here with respect to the previous question about additional sources of hydrogen. So this company called NewGen is actually, they are carrying out a green hydrogen feasibility study. And if I could just read from the document, it says here, hydrogen is a critical input in ammonia production. Currently, all hydrogen is utilized in ammonia production on the island is generated solely from steam methane reforming of natural gas. NewGen is seeking to produce hydrogen using a proven industrial electrolysis process that is powered by electricity obtained from carbon neutral sources, such as excess heat from existing simple cycle power plants, or from green energy sources, such as the recently announced Light Source BP Shell solar power generation facility. So there is some work into getting a different hydrogen source other than the natural gas. So you guys could look into that. The company is NewGen.
Okay. Yeah, we had a talk with NewGen a couple of weeks ago on the same green hydrogen. So thanks for mentioning that again. So people will see that DSP is in the right direction with this. All right. We have one more question. So on the same digitization and AI oriented question, right? You mentioned that you were doing remote monitoring. So in that remote monitoring, is there anything?
Sorry, Brian. Sorry to cut you across there. We're not actually doing remote monitoring, but we would like to go that way.
Oh, okay.
Yeah.
So out of augmented reality, virtual reality as well.
Correct. So it's just like how with the current way we work when this whole COVID thing came into existence, where most of the people would have been, well, if we want to call them non-essential workers, and we would consider like the operating core as the ones that actually have to physically be on the plant. Maybe a couple maintenance people, but the rest of guys and ladies would have been working basically remote from home. So in a similar fashion, yeah, there would be, especially for process engineers, you want to know if you're on call, do we need to actually go to the site? Do we need to leave the comfort of your home and go to the site to actually do your wrongs, or even in addition to find out like what's the current status of the plant? Do we have if we had a critical project going on and we need to follow it up over the weekend? We could actually log in, and it's something that we probably want to do in the future.
Okay, great.
Yeah.
Questions? Okay, I think we could probably give half 30 seconds for questions again. If anyone has any questions. Time. All right, so we have a thank you so much, Mr. James and Mr. Gobadan. We have a small token of our appreciation to show. If you could just unshare your screen, I'll present it to you next.
Give me a sec.
All right, I'll show.
Yeah.
Mr. James, I'm so sorry, Mr. Gobadan, that we didn't know of your presence before, but we'll definitely get something going your way. Mr. James, on your presentation, thank you very much for gracing us with this information and contributing towards the UTT SPE Student Chapter's goals and missions. So thank you very much. And we hope to have you back on this very segment again on something different and something that you could talk on again. Something that you have expressed your expertise in, just as this. So thank you very much.
Thanks a lot, I appreciate that.
Yeah. Thanks a lot to you all, guys.
All right. So everyone, do enjoy the rest of your evening, and we hope to see you soon again on another one of our segments. Stay tuned.
All right.
Take care.
Okay.